Okay, this video is going to be for Calc 3, section 14.2, which is regarding limits of computing limits for multivariable functions. So we're going to go ahead and take a look at notes here. Okay, so limits and continuity. We're going to really talk only about limits. I'll mention continuity, but we really don't include it in this class, although typically they are thought of together. Let me remind you of what we know about limits that we first learned back in brief calculus, and then again, I'm sure in Calc 1, Calc 2, AP Calc BC, this was covered in much detail. For a single variable function in calculus, we've studied the idea of a limit, okay? And the idea of the limit is if, as x approaches some constant or value in the domain, if the function value f of x approaches a value L in the range, regardless of the direction that we approach that value in the domain, then we say that the limit of f of x at x is equal to c is equal to that value that's being approached, right? So the idea is, if you have a function, let's say represented by this green curve, and we have regular y as a function of x, single variable function, right? Maybe we want to know what is happening to the output value of this function as we approach the input value 3, okay? And so maybe we could try plugging some values in as x approaches from below, from the left, we say, right? That means, like, if you had a table here and you plugged in some values getting closer and closer to 3, but not actually at 3, like 2.9, and you got 6.87 out, and 2.95, and you got 6.92 out, and 2.99, you got 6.998. It appears like if we got negligibly close to 3, we would be getting very close to the value 7. So since this is approaching the value 7, we say that 7 is the limit. And actually, that's a sided limit. It's a left-hand limit, so we write this way. The limit as x approaches 3 from the left with the little minus sign of f of x is equal to 3. So the limit number is the number that's being approached, even though we don't actually get there, right? That's the idea of a limit, okay? In fact, it doesn't matter if the function happens to be undefined at x equals 3. This is about the limit as what is y approaching as x is approaching 3. And then the same thing from the other side. If we wanted to say, let's approach from higher values, that value in the domain 3. Maybe we start at 3.3 and we get 8.12, and we plug in 3.15 into the function and we get 7.48. And we plug 3.01 in the function and get 7.002. This also seems to be approaching a value, and it happens to be the value 7. Right, so we would say the limit as x approaches 3 from the right of f of x is 7. Right? And then we said that as long as these two y values are the same, then that means no matter what direction we're approaching, the value seems to be approaching, the output value seems to be 7, right? So then we declare the limit as x approaches 3 without specifying the direction of f of x is equal to 7. Doesn't matter what happens at 3, could even be undefined, could be defined with some other value up here, like with a point, right? But it's what's being approached, right? So it's the y value. The limit is the value the y is approaching in the neighborhood of a specified x value, regardless of direction of approach. Okay, so that's what we know already about limits and how they work. And you have to check, basically you have to check what is the output doing as we approach from multiple directions. Okay, so that's what we're going to extend more generally now with multivariable functions. We're going to say, all right, for a multivariable function, let's take a function where we have one output, which is a function of 2 inputs, just to keep things kind of manageable, but this would be extendable into any number of dimensions for the inputs. If as xy approaches a point AB in the domain, f of xy approaches a value L in the range, regardless of the direction of approach, then we say the limit of f of xy at x equals c, actually that should be at xy equals AB. That's a typo in the notes. If you want to fix that, is L, right? And we would write it this way. The limit as xy in the domain is approaching the specific point AB of the function f of xy is equal to that single output value, right? A couple ways to picture this. One way is, if you know the domain is maybe represented as an xy plane, and we have a particular point AB in that plane. As we approach that plane, or as we approach that xy value from any direction, if up here on the output surface that represents the output values, those are all approaching some particular height here, L, in other words, there's a point x, y, l, then that L, that height, is the limit of the function as the domain approaches AB, okay? So you're approaching from any value, you get any value here. Right? Another way to think of it is to kind of write the domain and range separately. So you can think of the domain as the set of x, y points. And so maybe there's an allowable domain here. And within that, there's a point AB, right? So we're approaching AB. And then that domain results in a range of output values, right? And so there is some, as we get closer and closer to this point AB, whether it exists there or not, right? There is a value. If there's a value L that we're approaching, then this is the limit as we approach this point in the domain, right? And another way to express that kind of really precisely mathematically is to say, imagine there is a circle around the point in the domain that has a radius of lower case delta. And then there's a one-dimensional region around the limit in the range that has like a radius, if you want to think of it that, a distance plus or minus epsilon. Then a really precise way to state the domain is to say for every point A, B in the domain, there is a value L in the range, and for every plus or minus epsilon around the limit number, there has to be a circle that extends around that point in the domain, such that when the actual radius to any point in that circle is between 0 and that. In other words, if you're inside this circle where you have a radius between 0 and that radius delta, then you'll always stay within epsilon of the value. In other words, the function value minus the true function value minus the limit in the middle of this is equal to epsilon, or less than epsilon. So if you're in a small region around a place in the domain, you stay within a region in the range. Okay, we'll use that on one example just to show you how mathematicians demonstrate limits, but we'll not use that too much because that's a little more detailed than we usually get in the class. Okay, so here's another kind of representation for a function. Let's say we have x, y in the domain, and these numbers represent output values for different x, y pairs. And I have two functions here, f of x, y and g of x, y. Okay, so let's say we wanted to figure out what is the limit of the function f of xy as xy approaches the value x is 2, y is -1, which is right here. And actually, for whatever reason, the function's undefined, so there's a hole in the function right here, right? But if you look at what happens to the y value, or to the output value as I approach in this direction, it seems to be getting closer to the number +8, right? And as I approach in this direction, it seems to be getting closer to 8. And if I approach from this direction, it seems to be getting close to 8. As I approach from this direction, it seems to be 8. If I approach from this direction, it seems to be 8. Yep, it seems like it's approaching the number 8, regardless of what direction I come to this point from in the domain. And so therefore we would say, just kind of roughly looking at it, it seems like the limit is equal to 8. That's what's being approached no matter what direction we approach. Right? But if I did the same thing for g of x, happens to be undefined, you know, if I approach in this direction, the numbers seem to be approaching 8, and the numbers seem to be approaching 8 this way too. They're getting lower, right? But here's a problem, right? As I come from this direction, the numbers seem to be approaching a different value, -8, and -8 here, and potentially some other value here, maybe -6, right? So these are not all the same numbers, and therefore we have to say that there is no single value that's being approached. Something very weird is going on the surface here, where there's breaks or asymptotic behavior or something, because this is not approaching the same y value, or sorry, the same output value as we approach this value to -1 in the domain. Right? So that's another way to conceptually see what's happening, right? This limit doesn't exist, this limit does, because no matter what direction we approach, we always get the same value. Right? And so if we want to find a limit, we basically have to do something like this, except algebraically if possible. We have to try to approach the value that we're considering from as many paths as we can. And it's actually very easy to show. It's easier to show that something does not exist, because all you got to do is find one discrepancy here. And you can say, okay, definitely the limit doesn't exist. It's much harder to do this, because technically you have to approach from all possible directions. And it might be easy to approach from some directions, but at a certain point, you just have to kind of say, well, it really looks like it is. There is a way for us to conclusively show that this is true. And we'll show you that here on the next screens. but does hopefully this makes sense. The idea that if you get the same value regardless of path, then that means the limit exists. Okay, so how do we find the limits without resorting to just listing values out like that? We could try approaching from different directions, which are easy to compute. And it's, like I said, easier to show that limits don't exist, okay? To state a limit does exist, in practice, we go ahead and test a variety of cases, and if they all seem to be approaching the same value, then we use the squeeze theorem, also called the sandwich theorem, and two functions that are bounding below and above, to show that if those two bounding values are approaching the same limit, then the actual function in between the two is approaching that. So what I'm saying is we're going to, let me go back to the graphical representation. We're going to say, all right, I can't in this domain reasonably approach from every direction, but I might do things like say, let's approach in the direction of the y-axis. Let's approach in the direction of the x-axis. Maybe we could define a parabola like y equals x squared and approach that way. Or we could do x cubed curves or something like that. Just anything we can think of that where I can kind of find an algebraic representation of a path and then approach from that and see if the limit ends up being the same every time. Okay, so the best way to see this by far is just to work examples. So I have quite a few examples here for us to look at today. All right, so let's say I want to find this limit. The limit as xy approaches 0, 0 of this structure. Okay, so the first thing we would do is maybe just try to plug in, right? If the function's really well behaved, that might work, you know, and even in this case, let me go way back to the single variable case. Before we bothered to compute all this kind of stuff, right, the first thing we did was if we had an algebraic representation, we just went ahead and plugged 3 into the function to see if we got 7. Because if we got 7, that means the function is well behaved enough that we could just obtain the value that's being approached by plugging in. So we usually try plugging in first, and then we resort to path tests if we can't. So let's see, if I plug 0, 0 in, well, I would get 0 over 0, and so that's an undefined expression. If you happen to get that, you could try other things, like you could try factoring, you could try synthetic division, rationalizing if there's radicals, trying to see if plugging in works. Note, L'Hopital's rule, unfortunately, cannot be used because you know, I don't know to what degree it was defined. I know when we talked about it in brief calc, we were very loose about how it was defined, but L'Hopital's rule is only defined properly for single variable functions. So there is no multivariable version of L'Hopital's rule. So if you can't think of some clever way to factor and cancel and stuff like that to making plugging in, you can't resort to doing the L'Hopital's and take the derivative of the numerator or the denominator. So we're going to have to use our path method here, right? And so let's just pick some paths, and I'll show you what I mean by that. So let's say that I consider the approaching this point, but along the y-axis, and the y-axis is where x equals 0. Right, so all I need to do then is just go ahead and substitute 0 into this. So I'm taking the limit as xy approaches 0, 0 of, if x is 0, this is negative y squared over y squared, okay? Which I can factor, and that's going to be the same as that limit as xy approaches 0, 0 of negative 1, and the limit of any constant is the constant, and so that would be negative 1. So I'm able to compute that the limit along that path is negative 1. Okay, so let's take a different path. Let's take the path the x-axis. That's the next easiest one because that's just plugging 0 in for y. So if I said, what's the limit as xy approaches 0, 0, and I plug 0 in for the y, I'm going to get x squared over x squared, which is positive 1. And I can already see that since those two things are not matching, just from these first two directions I checked, that means that this limit does not exist because I'm not seeing a single value that's being approached depending on the pathway. Okay? Okay. Yeah, what this is equivalent to doing is saying, okay, let me see if I can make a little sketch of it to make it clearer. We've got x, y, z, right, where the domain is x, y. We're trying to approach a value 0, 0. So we're coming up on 0, 0. And what we just did with that blue thing is we said, let's approach along the y-axis. So let's force x to be 0 as we approach in this direction, right? What do we get? Well, when we plugged in, we got the value -1 when we did that, right? But when I approached in this direction, I got +1. And that means that, you know, the function is doing something different, right? It's got to have a very strange looking surface to be approaching a different z value as we approach this way compared to this way. And we know that at this point itself, there's a hole. So the function must be doing something really weird. Okay? Anyway, this is the kind of method we use. We pick some things that we think are easy to substitute expressions in for x and y to define a pathway in the domain. And then we try to compute using plug-in, maybe factoring. So what we did here is factor and cancel things to try to evaluate. All right, let's try another example. So let's say we have this limit of this structure. We try plugging in, and again, we get 0 over 0. So we're going to have to do pathways. So maybe for this one, we can try our y-axis first. That's x equals 0. And so we would get limit as xy approaches 0, 0 of, let's see, if I make x 0, I'll have 0, and then this will be 0 over y squared. And that's actually equal to 0, right? That's not undefined because since we're only approaching 0, y is not actually quite 0. It's close to 0, but it's not 0. So 0 over a small number is still 0. So that we can compute that limit on that pathway. Okay, for the x-axis, let's try that next. X-axis is where y would equal 0. So if we did limit as xy approaches 0, 0 here, but using y as 0, then we would have 0 over x squared, which also is 0. So far it's looking like maybe it's 0. So let's try another one. So the next simplest thing we can do, other than just plugging zeros in, is we can pick a line. Okay, so let's try that. We'll try a line. And for a line, the simplest way to express a line is y equals mx. Okay, I'm just going to try that line right there. So what I'm going to do is substitute m times x in for y into the limit expression. Okay, so this will be x, and then the y will be mx, substituting for this y, and then I have x squared plus y squared is mx squared. Okay, so what do I have here then? I've got mx squared, and then I have x squared plus m squared x squared, which that means I could factor out an x squared on the top, right? And I would be left with m. And then I could factor out an x squared out on the bottom, and I would have 1 plus m squared left. And so when these cancel, I'm really taking the limit as xy approaches 0, 0 of m over 1 plus m squared, where m is some slope. And potentially for a line, it would be other than 0, right? So if this was some slope other than 0, then hopefully you'll agree that this would not be 0. It would be some constant that isn't 0. And since that does not match the two things we had before, this is another case where we've shown that the limit does not exist. Right? This limit does not exist because I can pick a path that has a non-zero output value that's being approached, and yet these two paths have zeros. Okay. All right, so that's another example. Let's take another example here. A little bit more complicated structure. We're still approaching 0, 0, which makes it kind of nice. Let's go ahead and, yeah, if we plug zeros in, we get 0 over 0 again, of course. So let's try some things here. Let's try y-axis. Okay, so y-axis is where x is 0. So that would be a limit as xy approaches 0, 0 of, let's see, if I plug x in for 0, I would get, or 0 in for x, I would get 0 on the top, and then y squared, which we know is equal to 0, right? I could do the y-axis, which would be y equals 0, and I would have the limit as xy approaches 0, 0 of 0 over x squared, which is also 0, okay? Let's try the lines. We tried lines. Lines would be of the form y equals mx, and so if I did that, I have limit as xy approaches 0, 0 of, let's see, 3x, or x squared, but then this y would be mx, Then I have x squared plus mx squared, right? Which would be that same limit, but it's going to be, so it's going to be 3mx cubed. So you know what? I could factor out an x squared. Let's do that. Just trying to get this so that I can plug in things and try to evaluate to a constant or a 0 or an infinity or something like that. So if I factor out an x squared, I'd be left with 3xm. And if I factor out an x squared on the bottom, I'm going to be left with 1 plus m squared, right? But that means that if you took this limit and you plug a 0 in for this x, we're going to get 0 over 1 plus m squared, which is presumably not 0. And so this is also 0. So now the line pathway also produces 0 for the output value. Okay, so I got to bump this up to something else. Let's try another one. Let's try a parabola path, parabolic path. Y equals ax squared, right? Some ax squared kind of thing there. So that would be, let's say, limit as xy approaches 0, 0. So I have 3, I have x squared, and for the y I have an ax squared, okay? And then x squared, and then ax squared being squared. So let's see, I'm going to be able to factor, I think, just an x squared out. So let's take an x squared out on the top. And I'll have 3ax squared left. And then if I take the x squared out on the bottom, I'll have 1 plus a squared x squared. Right, so this cancels. And if I take the limit and I plug a 0 in here, let's see, I'm going to get 0 on the top and 1 on the bottom, which is 0 again. And that means that, okay, I keep getting 0. What if I did a parabola the other direction? So let's do another, I'll pick a different color. Let's do a parabola that's in the other direction of the plane. X equals a y squared. Okay, so limit as xy approaches 0, 0 of, let's see, we had 3, and then we would put a y squared in for that x and then y. And then this would be over, this x is ay squared squared plus y squared. So again, I think I can only factor a y squared out. If I factor a y squared on the top, I'm going to be left with a 3, an a squared, the other y squared, and a y, which is y cubed. And then I'm going to have here, if I have a y squared on the bottom, I'm going to have, let's see, a squared, the other y squared, and 1. And so now if I plug in 0 for this y, I'm going to get 0 over 1. So that's 0 again. And so it seems like all these paths are always resolving to a limit of 0. Okay, so at this point, we would say, all right, run up the flag, right? Little white surrender flag, I give up. The limit is probably, it's probably equal to 0. Okay, but I can't be sure yet. Okay, so we have to do one more step. If we do this and we come to the conclusion that they're all approaching a value, then we have to take a more formal approach. Okay, I'm going to show you two ways to do this. And the first way, we're not going to actually do this way. We're going to do what we're going to do on the second slide, but to show you the way a mathematician would proceed at this point. So if you're going to become a math major, or get a math minor, and you take a proof-oriented calculus class, which would be required for a math minor, this is the way mathematicians would solve this. They would say, okay, we think the limit exists and it's 0. To be sure, we're going to use this more formal definition that we did back here, that we said, okay, if the limit exists, there's a circle around the point in the domain with radius delta, such that if the actual radius is inside the circle is between 0 and delta, there exists an epsilon such that the difference between the function value and the actual limit magnitude is less than alpha, or epsilon. So if you can show that there's an epsilon when this is true, that this stays within, then you've shown that the limit exists. Okay, that's a very, very formal way to think. And I think they dropped, these are called delta epsilon proofs. They used, when I took calculus in the 1980s the first time, they used to always include those. But my understanding is that even in AP Calc BC, they may not do delta epsilon proofs anymore. So maybe this is new to you. But But so basically what we're going to do is we're going to show that if this is true, you can find an epsilon such that this is true. And if you can show that mathematically, it means you've proven without beyond a shadow of a doubt that the limit is indeed 0 and would be 0 no matter what path we took. So we're going to say let epsilon be greater than 0. We want to find a delta, so it's actually the reverse. We set this to be something, some positive value, and go looking for a delta that would make that true. Okay, we want to find delta that's positive, a radius in the domain, such that if the actual radius stays between 0 and delta, then the function value minus what the limit we're attempting to find, which we think is 0, is less than epsilon. Okay, so here's how we do it. We're going to choose, we're going to take the function, and because I want it to be less than some positive value delta, I'm going to first just take the original function but put an absolute value here to make sure that we're dealing with positive values, because we're talking about distances from a point, okay? And then we're going to notice this kind of clever thing here, that in the middle of this function, there's x squared over x squared plus 1. Right? X squared over x plus squared plus 1 will always be, that should actually be less than or equal to 1, right? Because if y was 0, then this would be equal to 1, but if y is anything else, this fraction will be something less than 1, okay? And what that means is that this whole expression is going to be less than or equal to that expression with this replaced with the 1. So this whole expression is less than 3 times y, where we have y as an absolute value, okay? And we can say, let's see, that's the same as saying that you could get that magnitude by taking the square root of y squared, right? And therefore this is less than this is less than 3 times the square root of x squared plus y squared, because by a similar argument, y squared has to be less than or equal to x squared plus y squared, because this would be equal in the case that x is 0, but less than in any case. So we've got these three things, really three things, this and this and this, where this has to be less than or equal to this, and this has to be less than or equal to this, okay? So we know that we're trying to define a delta such that square root of x squared plus y squared is somewhere between 0 and that delta, right? So if we just go ahead and set this side out here to be 3 times epsilon, right? In other words, we're going to say that this epsilon over here, sorry, this epsilon here, I misspoke, would be 3 times delta, because this square root of x squared plus y squared would be the delta. Then this structure here is less than 3 times delta. Then that means that we can say that the original function is less than 3 times the square root of x squared plus y squared, which is less than 3 times delta. And that means we've shown that the difference between this and 0 is less than that epsilon, as long as we choose epsilon to be 3 delta. Now that is super convoluted, right? This is the reason why I didn't become a mathematician. To me, this is weird to think this way, but now some of you might be going, yeah, that's super obvious, and I kind of like that. It's really clever, and it's really formal, and you can kind of step-by-step walk through this. This is basically a proof, right? And so if you take proof-based calculus and you become a mathematician, this is the space you're going to live in. This is what you do, this kind of stuff. You're trying to show without that in all cases, no exceptions, right? This is true. But this is quite a bit for applied mathematics students to deal with. So we have an easier way it's actually just as good, but it's a little less formal. And it's called using the squeeze theorem or the sandwich theorem method. Okay, and the idea is that if we think that that this is close to the value 0, that the difference between this and 0 is very small. In other words, that the limit is this value 0 because the difference between that would be small. Then we can just go ahead and replace this with absolute value. Use that same trick to notice that there's this part in the middle here, right, that we know has to be 1 or less. And then say, okay, if that's somewhere less than 1, then that means that the original function, slightly modified with the absolute value, the original function is going to be somewhere between 0 and the function 3 times y, because absolute value of y, because I'm replacing this with a 1. It can't be anything larger than 1. And that means that if we take the limit of this side as we approach 0, 0, and we take the limit of this side, and they both are the same value, then they're both squeezing in on this one, and this cannot be anything other than that limit. So in fact, if you take this constant 0 and you take the limit as xy approaches 0, 0, you get 0. And if you take the limit of this function as xy approaches 0, when you plug 0 in for y, you get 0. And since this function has to be in between these other two functions, there's no way for the limit of this function to be anything other than 0, because it's being squeezed. Sometimes it's called the sandwich theorem, sometimes the squeeze theorem. So I know that theorem was discussed in AP Calc BC. And therefore, because we can show by the squeeze theorem that this function is limits 0, then therefore we would have gotten 0 no matter what path we went on. I think we're going to just do one homework problem that's done that way, and I'm going to ask you not to do it this way, but with a delta epsilon proof, but instead to do it using the squeeze theorem. Okay? All right. Now, usually at this point, when we cover limits, usually we also talk about continuity, right? The idea being that, let me go back to the visual image of this, right? If you have, as we're approaching a value from any, in the domain from any point, that we're approaching a value in the range and getting a particular, in this value height L, z value is some limit, that that will happen when the surface here is smooth and continuous, right? Smooth and continuous meaning there's no discontinuities or jumps or gaps or anything, right? And that's easier to determine with single variable functions, right? We had tests, like we said, all right, we could, first of all, make sure that if you plug the x value for the domain value into the function, you get a point. The point exists, right? And you can evaluate the limit from checking all directions to make sure the limit exists. And then the third thing we had to say is the y value for the point has to match the y value for the limits, because that way we know that the point is filling in the hole, and therefore this is smooth and continuous, right? So that's easier to do when we only have to approach from a particular direction, right? But there is an analog of that in multivariable calculus, the idea being that if you wanted to check if something is continuous, then a function is considered continuous if it's true that the point xy changing by a small amount, if that's true, then the value of the function changes by a small amount, meaning that the surface has no holes or break above this value in the domain, right? And the way we check it is by verifying and computing the limit of the function, right? We have to go through all the steps we did before to prove that it has some sort of a function. And then we have to say that that resulting function for the limit in the vicinity is well behaved. In other words, the function itself has no discontinuities in the range of the xy that we're considering. So the textbook definition is a function f of two variables is called continuous at the domain point AB if the limit as xy approaches AB of the function results in a function that you can use to evaluate the limit, and that function is continuous over the domain at every point AB in the domain. Okay, now if you really want to, know more about continuity, we're not going to include it at all in the course. I just mentioned it for completeness, but if you're interested, send me an email, and I'd be happy to copy the pages related to continuity from the textbook and show you that. But Ms. Dastu last year did not. She just mentioned that continuity is part of it. She didn't even include this in the notes, so it's not considered formally part of the course. All right. Couple of hints for homework tonight. Number 13, it's the only one that's going to require the squeeze theorem, right? All the other ones you should be able to just do by path checking, okay? And then for number 17, you can try a conjugate because there's a radical. Let me take a quick look at number 17 just to see if I can show you what that looks like. Let's see, 14.217. Make sure I'm talking about the right problem here. Yeah, okay. Whenever you have a limit like this, let me actually show that. Whenever you have a limit that's like this, right? We always try plugging in first, right? And if we plug in, we're going to get 0 over. Actually, in this case, I think. Yeah, we could say 0 over, oh, that's the problem. It's going to be 0 on the top, and this is going to end up being 1 minus 1 is 0. So we're going to have to check paths, right? Well, before we check paths, if there's other algebraic techniques you can use that will allow you to successfully plug 0, 0 in without dividing by 0, you can try those first. And this goes way back to brief calc. This is in the form of conjugate. So if you were to take the side with the square root and multiply top and bottom by the conjugate of that, you copy this term and this term and you change the sign to plus. And we can't change the function, so we have to multiply top and bottom by the same function. When we multiply all this out, leave this one the same, but when you multiply this out, it's going to result in the square root being removed, right? And there's a chance that what we're going to get is going to turn out to have x squared plus y squared factored out of it. And if that's true, then that means you'll be able to cancel off the part of the bottom which is dividing by 0, and you will in fact be able to plug in. If you can plug in the domain values and make it evaluate to a number instead of to something that's 0 over 0 or undefined in some way, then that is the limit, right? So this is what is meant by using the conjugate. All right. Okay, that's it for 14.2, and I know that was a pretty intense lesson, but give the homework a try based on that, and we're going to spend a day talking about homework questions after this, because I think this is one of the harder sections in 14. So we'll devote a second day to this in class to look at examples.